Thank you for being here. My name is Richard, and today we have Kelsey. Also, she's back again, our beloved tech artist. She's got amazing earrings on today. Yeah.
Today.
And we're very fortunate today. We have Adam Mars. He's a principal graphics engineer at NVIDIA to talk to us about RTX Mega Geometry and help us understand what this technology is all about. It's currently released in NvRTX 5.6, and there's a lot to discuss about it. So, thank you for being here.
Thanks for having me.
Yeah, awesome. I guess we just jump right into questions. So, high level, what is RTX Mega Geometry all about? Especially in the Unreal Engine. I know we had it as it exists outside that as an SDK, as its own software, but then it moved into Unreal, and it's meant to work a certain way in the engine. So help us understand what that's all about.
Yeah, so RTX Mega Geometry, or Mega Geometry for short, that we often call it.
Yeah.
It's kind of a collection of features, and those features and performance enhancements are aimed towards ray tracing acceleration structures, making it possible to ray trace much higher fidelity geometry than you were able to do in the past. So these are some slides from a talk I gave earlier this year at GDC. And in the context of Unreal Engine 5, there are a lot of things that change in the engine since Unreal Engine 4, and Mega Geometry is sort of purpose-built to help solve some of the problems that came about with UE5's introduction. So UE5 introduced Nanite, which is a really cool level of detail system that makes it so that geometry is virtualized and clustered. And they do this really cool trick where they can dynamically select clusters based on your view and eliminate that annoying LOD pop that you get with geometry. And today, this works really great with rasterization. But back when the ray tracing APIs were originally designed, Nanite didn't exist. And so they naturally didn't design the APIs with Nanite in mind. And so the geometry, the way we represent geometry in ray tracing is with a bottom level acceleration structure, or BLAS. And with Nanite, that BLAS has to change constantly, all the time, as you move around and as the LOD changes. And that gets really expensive with the existing APIs. And so in the engine, they have to solve this problem somehow. And the only solution that DXR natively provides is for them to just not use the same geometry. And so in UE5, when you have a static nanite mesh, instead of actually having the full nanite triangles like you would in raster, in ray tracing you have this proxy mesh that's some low detail approximation that never really changes. And so this creates a problem where rasterization and ray tracing actually use different geometry, and that creates visual problems, self-intersections for shadows, just incorrect shadows, and then in reflections, the geometry doesn't look as detailed as it does when you're looking at it in the primary view.
Yeah.
And there are a variety of workarounds and stuff that Epic has done to try and mitigate these problems, but none of them really solve the problems. And that's ultimately where Mega Geometry comes in. It makes it so in ray tracing, you can use the full quality nanite triangles instead of that proxy. So to just give you a visual example, because that was like a whole lot of talking, here is what a scene would look like in UE5 without Mega Geo when you have ray trace shadows turned on, and you have really detailed nanite objects casting a shadow. The proxy mesh is just some very low detail representation, and the shadows don't look great as a result. So you can see kind of facets, and for things like trees, the leaves, they become just like these big triangles. And then if you look in the reflections, the trees are also a bit of a muddied kind of mess. And you'll get self-intersection, false occlusions in places too that I'm showing here on the bush. But if you turn on Mega Geo, you can fix all of these problems. So if I just go back and forth, so before with Mega Geo turned on, you'll see that the leaves in the foreground and the railing shadows are now perfect. They're exactly what you would expect. Our reflections look like they should. They look like a tree, a high detail tree is there. And then our self occlusions on the bush in the left go away when you have Mega Geo.
Right,
So
and those were images from the Zora project too, right? So that was Unreal 5.4.
yep,
That was the first time it got implemented, right?
that's right. Yeah. So for CES, where we showed Zora and showed this content, the initial implementation was done in Unreal Engine 5.4. And since then, we've moved to 5.6. So yeah, at a technical level, Mega Geometry is really this collection of a couple different features that make it so you can build acceleration structures way faster than you can with regular DXR as it currently is. And you can do this without a lot of CPU overhead, and you can build up to 100 times faster. So you can use way more geometry as a result.
Yeah, this is really you don't have it. Oh no, you do have it. I guess you don't have it on this slide. This is real interesting to me though, because the whole time we've been, anybody who knows anything about ray tracing in Unreal Engine, probably just ray tracing generally, you're familiar with the concept of these acceleration structures, the top level and the bottom level acceleration structures, or the TLAS and the BLAS. And in order to do Mega Geometry, a third acceleration structure needed to be added, or a new one, and that's the CLAS, right?
That's right. Yeah. By adding the CLAS, we were able to essentially change the way the algorithms run and make the processing of the geometry way more efficient as a result. So when doing ray tracing, both when you're building those acceleration structures and when you're tracing them, that addition of the CLAS acceleration structure changes things in a really important and big way.
Right. That stands for the cluster level acceleration structure. Is that right? Or
That's right. Yep.
okay, cool.
Interesting. Okay. Hey, can we go back a couple of slides to the first slide where we're showing the proxy mesh in the shadows? Yes. So
Here.
yes, that one. So what is the difference? Because I know that even without Mega Geometry, there are some ways to mitigate this kind of artifacting that we see. It could be here, it could be in self-shadowing even, and we would use raytracing.nanite.mode1. And I believe what that does is it'll use the full resolution mesh, or like the higher resolution LOD mesh for the fallback, as opposed to like the lowest quality fallback. That way we're not getting all of that self-shadowing. What's the difference between that and RTX Mega Geometry?
Right. Yeah. Good question. So Epic has sort of this built-in nanite ray tracing mode. And the primary difference is that that mode uses only what DXR can provide. And DXR and its APIs weren't designed for these clustered geometries that Nanite has. And as a result, like when it's building its BLASs and its acceleration structures, it's a lot slower at doing that. And so the mode itself, like there are a lot of little nuances in terms of how it's different than how we do things in Mega Geometry. And I'll try and avoid the like graphics programmer weeds there to not like make everybody fall asleep, because there are
might be some
some
graphics programmers, tuning in today. It could happen.
there
Maybe not
are
most
some
people
differences,
though.
and they are meaningful in terms
Yeah.
of what level of detail is used and like what's streamed in and all that stuff. But the important part is that no matter what you do with DXR11, it can't build acceleration structures as efficiently as what is offered by Mega Geometry. There's more CPU overhead, and because those bottom level acceleration structures have to change a ton, like every frame, every single one would change. So you have to rebuild every BLAS every frame. It's really slow as a result.
Yeah.
And so the main purpose, at least as of now, for that built-in Nanite ray tracing mode is really for Epic's path tracer. So for high quality cinematics and stuff, they can turn that on and it'll push way more geometry into the BVH. And it doesn't really matter as much that it's slower in doing so. It's really all about visual quality. Whereas with Mega Geometry, you can get both. You can get that super high quality geometry, but you also get way better performance.
Right. What sort of compatibility does platform compatibility does Mega Geometry have?
Yeah, so in terms of compatibility, all NVIDIA RTX GPUs.
Right.
So that means all the way back to RTX 2000 or Turing. And so that means Ampere, Ada, and then our new 5000 series Blackwell GPUs, all of them support Mega Geometry. As you might expect, like your older GPUs aren't going to run it as fast. And GPUs that have slower memory or less memory won't be able to use it for large worlds and stuff.
Right.
And for example, like Blackwell has specific hardware to help with this problem. So the amount of memory that the new, like the CLAS acceleration structure takes will be less on Blackwell than it would be on our prior architectures, because Blackwell has some goodness in there for that.
Sure.
So yes, that's basically, yeah, RTX GPUs up and down the stack, works everywhere.
Right, and it's tied to some driver version as well, right? There's some driver component to it, so you
Yes.
probably need a minimum driver level
Yes.
in order to get it to work.
Yeah, I'll say like use the newest driver,
Right.
just as a general rule.
Yeah.
But I think our drivers since Blackwell release have supported Mega Geometry.
Yeah, that makes sense. Okay.
Yeah, so since January of this year.
But when RTX Mega Geometry came out, it was part of the NvRTX 5.4, let's call it the Zora experimental branch. Have there been any improvements or updates? Or I guess a better question would be, what changes are there between 5.4 and the latest implementation in, I guess, mainlined NvRTX 5.6?
Yeah, so you should definitely use the new one. Like the 5.4 experimental branch was very much experimental and very much for people to just see like, hey, this is how we did it. This is how Zora works. But there was a lot of stuff in there that was kind of specific to Zora. And with the release in NvRTX 5.6, we wanted to kind of tighten that up a little bit and make it more focused. So there are a few things that were in Zora that are not in the NvRTX 5.6 branch. For example, primary ray tracing is not included in the new branch because that was just a very special feature for Zora, for the Zora demo. But what you get instead is a lot of code improvements and bug fixes so that the code runs better. It's kind of easier to understand too, makes more sense. And we added support for Mega Geometry in inline ray tracing, as well as building acceleration structures of all types, CLAS, BLAS, and TLAS, in async compute.
Okay, so at a high level, I build my scene with Nanite, and I can sort of inject it into the CLAS. I can make use of Mega Geometry and have it fully rendered in ray tracing. I can have the shadows fully there and reflection is fully represented in reflections. Does that come with any limitations on content? Like, I know one of the shortcomings right now with the technology is we're doing static meshes. We're not doing skeletal meshes yet. Or maybe I shouldn't say yet. I don't know. How would you characterize that? Is that a current limitation? And then, you know, how is that sort of thing going forward, do you think?
Right. So I think, you know, this gets to an important point, which is even in NvRTX 5.6, the current implementation is still marked as experimental.
Right.
So it's not beta. It's not like, you know, full release. It's experimental still. So it's better than it was.
Yeah.
But there are still limitations, both from an authoring standpoint and an efficiency and performance standpoint. So we support static Nanite meshes. So you can drop those in. You can make them, you know, ISMs and instance them everywhere. You can use the foliage tool, and that all works. But skeletal meshes are not supported yet. Effects like
and that is a new thing. Like Epic, I don't remember what version that came into existence. It was either 5.4 or 5.5, but it just came into existence basically.
5.5 included support for Nanite in skeletal meshes.
Right.
So that is fairly new, and we don't support it yet. Things like WPO are not supported yet.
Right.
But for objects like characters, like in this shot, that, you know, need to be skeletal meshes, you can have them as regular triangles, non-nanite meshes. And in the BVH, you can have both. You can have both Mega Geometry doing clustered BLASs of nanite meshes, and then regular geometry that's being skinned like characters. So like in Zora, you know, we showed both working at the same time.
Right.
In the future, it would be, you know, very nice to have that support for skeletal meshes working, and that's something that we're going to look into. But for the moment, our main priority is getting optimal performance, optimal memory for using this with static nanite meshes.
And if anybody wants to reach out to us for anything related to NvRTX, this feature or other features, I just put our contact email. That actually goes to the whole NvRTX team. So I would see it, Adam would see it, Kelsey would see it. You know, we can help address any questions you might have. Maybe if we don't talk about it in this episode, you can just reach out to us directly that way.
Yeah. Yep. And we will have a Q&A too. So
yeah.
Adam, question. So considering, let's say I have my own engine source that I'm developing off of, I've implemented my own stuff and it's based off of 5.6. Would I need to take NvRTX like wholesale, or is the implementation of Mega Geometry contained enough for me to be able to maybe a large cherry pick things over or patch it?
Yeah, good question. Yeah, you could certainly take all of NvRTX and build off it if you wanted to, but something we try to do pretty hard in NvRTX is make it so the individual features can be cherry picked. So if you want to pick and choose the thing you want, you can do that. The cherry pick of Mega Geometry is just one commit that you can pull, and you'll get everything in there. So yeah, if you're working in 5.6, you could just take this feature if you're not able to build, you know, off of the entirety of NvRTX. One of the things that I made sure to do is that all the Mega Geometry code is wrapped in a preprocessor define. So if you search for that define, once you've pulled the code, or if you're looking at the branch, search for that define and you'll see every single change that goes into MegaGeo. And this also makes it so you can compile out the entire implementation. So if you're having bugs or issues after you've pulled it in and you're just like, I'm not sure if this is conflicting with something else, you just compile it out. And you could also compile it out for platforms that don't support it. So yeah, it's I hope pretty seamless to pull and use, and things are very clearly wrapped so that you can see where everything's being done.
Yeah. What about the current implementation? Are you looking to improve or refine or make better? I mean, like for example, I know right now you you might need to make, sort of inspect your environment, look for hotspots, and
Yeah.
then set your memory values. And you've talked about this being something that you want to improve. So is that something to focus on, or are there other things, or yeah, what would you say about all that?
Yeah. So one of the aspects of the experimental tag when it comes to a feature is that it hasn't yet been made super user friendly yet.
Right.
So there are a variety of CVARs related to the implementation that you'll want to set and tweak, and they're not exposed in the editor yet. So there is a debug UI that pops up, or you can make pop up when you're using Mega Geometry. And when you guys show an example of a scene, you can show that, and that UI will tell you a lot about your scene and about what MegaGeo CVARs need to be set and what their values should be. But there is going to be some amount of tweaking you'll have to do in this experimental state, where you're saying, yeah, use this amount of memory for BLSs, use this amount of memory for our CLS streaming pool. I know that I'm going to have this many objects in the scene that I need to be built for ray tracing. There's a little bit of that you've got to do to massage it at the moment. And in the future, absolutely want to iron that stuff out so it's either completely automatic, so you don't have to do anything, or at the very least, it's just whittled down to just a couple easy things, very straightforward things to specify.
Right.
That
So
was fast.
this is the scene we will be releasing soon. And I don't want to steal Kelsey's thunder, because this is really her scene. She's the primary architect of this scene. But this is the Bonsai Demo, and it takes advantage of RTX Mega Geometry. So you're looking at millions of triangles being rendered using nanite triangles being rendered using this new system. And it'll be in NvRTX 5.6, and it's also taking advantage of other features of the branch like path tracing and DLSS4. So it's a kind of like Zora in the sense that it's a little bit of an everything scene, but the focus really is on Mega Geometry. We want to show what we can do with Mega Geometry, and not a super expansive scene, but a tight little scene, and make it easier for people to download. So as a large download, this is a more focused project. But you can see, a lot of neat features, rendering features are being used. But yeah, I don't know. Like I said, this is really Kelsey's baby. So, do you want to say anything about it at this point?
Well, number one, we're going to have another webinar, Richard and I,
Yeah.
and we're going to be talking about this more in detail. So come to that one if you want to
Right.
see. If you want to see all the pretty colors too, because I made sure that we had. Richard made sure that we had, because he did a lot of the lighting, actually, all the pretty colored shadows and whatnot. But yeah, that's part of it. Now, I guess we could get into like how certain things were constructed. And this is more along the lines of what we found to be optimal for content creation for Mega Geometry. And this could be argued too for Nanite as well. But things like this bonsai tree, for example, ignore the ivy for a second and focus just on the bonsai tree, like the bark itself, and the leaves in the tree, like those leaves on the left, the different fronds and different things like that. Oh, yeah. You can pause.
Can you guys see that video paused?
Yeah, it's perfect.
Yeah.
Yep.
Cool. So
yeah,
we can just look at it for a second.
Yeah. So a great example is let's just take a look at the bonsai tree. Now, this bonsai tree that's placed in this level is actually a blueprint that has instant static mesh components. The bonsai tree itself, the large branches that are coming off of the tree. That's all one like monolithic, asset. That right there is pushed into the project as an FBX, your standard static mesh, and then it's converted to an instant static mesh within the blueprint actor that I created. There are 3 different types of leaf variations, for lack of a better word. And those leaf variations are instanced around about like 150 instances each. One's like 178, one's like 115, the other one's like 150.
Yeah, you get
for all
hundreds
3.
of these leaf groups all
Yes.
over this thing, right?
Yes. And so the tree itself, plus all of those instances, packed in a blueprint actor, then placed into the level, allows us to manage the memory better when it comes to streaming. And this is specifically for Mega Geometry, but it's also good to do this just generally speaking for memory management. Now the same thing for not just the bonsai tree, but the eucalyptus trees that you saw a little bit earlier. Those eucalyptus trees are built the same exact way, albeit they don't have the same amount of instances because they're not hero props like the bonsai tree is. But they are similarly put together in a way where it manages memory more efficiently when you place them in the level. The ivy, those are just standard static meshes that are placed in the scene. And we could turn them into blueprint actors and just place them in there. But this is trying to show the different ways of putting content together to really show how to manage memory with Mega Geometry best. So this is a great example. I don't know how much you're going to get into this video show through, but this shows right here the differences in the visualization in the BVH without any material evaluation. You just see what the mesh is. And if you turn on and off Mega Geometry, you're going to notice that with Mega Geometry on, you're getting the full detailed nanite mesh. When you turn Mega Geometry off, you're going to see a lot more like faceting, a lot of leaves missing, and just overall like lower resolution nanite meshes. So this is another visualization mode that's part of the whole RTX Mega Geometry implementation that allows you to develop with RTX Mega Geometry. So you can see exactly when you're putting things together in your level, how are things working? How does it look? How is it improving, etc. So I know I went on a tangent there. We were really talking about the stats, but you got me going.
No, you're good. I realized too, I'm showing some pre-recorded video right now. I kind of buried the lead with this. This was captured off of a 5060. So an 8 gigabyte 5060 graphics card.
That's
so
right.
Just to show, we're trending. We don't have the project released yet. It'll be in a few weeks if everything goes right. But we're trending towards having this be demonstratable on as wide a range of hardware as possible.
Yeah. So for Zora, the main scene that we showed at CES, that was running on a 32 gig 5090.
Right.
So it's granted they're different scenes and stuff, but it's very cool for it to be running on an 8 gig 5060.
Yeah.
And this is using, if you look at the FPS counter at the top as well, we have not dipped below 100 FPS at all. And this is 1080p, right?
Yeah, there's some DLSS running. So
yeah,
because it is a 5060. This is not a. If you wanted to load the scene up onto your 5090 and we can take a look at it there, we can do that too.
Absolutely, we can. Yes.
Yeah,
yep.
So,
we're going to stick to 1080p windowed mode just for now, so we can show you guys. We'll load into
maximum
the level.
frame rate, I imagine.
Oh yeah, there you go. All right, let's see. So let's open up the stats. Let's pause it here. We'll keep an eye on this scene right here, and we'll open up the stats on the left. So the stats that we were talking about earlier, when I was asking Adam, the debug UI, because we're asking folks to set their budgets based on their particular project. And, how do you do that? Like, what's the magic number? Well, what I love about this is that the debug UI, well, you have to get into it and take a look at it. And all of that information on how to look at the debug UI is within the documentation on the NvRTX 5.6 branch. But it's everything that you really need to look at and focus on is under summary, the summary category, and underneath budgets. So what these budgets will do is, as you're developing within the editor in your project, you're going to want to fly around, get into different viewpoints of your scene, especially in areas where it's like really dense, heavy nanite geometry or just everything. Just start flying around. And you're going to notice that these numbers are going up. And as these numbers go up, and then eventually stabilize, that's when you know, okay, this is my budget. These are my budgets that I want to set in my default engine INI for my project at that time. Now, again, this is always going to change, especially if you're adding more geometry, maybe taking away more geometry, maybe you're optimizing more, maybe whatever else. You're going to want to do this again so that you get the actual baseline. I can tell you this, during the course of the development of Bonsai, the Bonsai diorama, we have set budgets at least 5 times because we were trying to make sure, like, how are we doing, or how's everything looking? And we found that the current budgets that we have set now, which is what you see here, are decent for the project now that the project is finished. But this is what I was mentioning on, it tells you. And you
and Adam, this is really the part of it where you imagine in the future this will be more automatic.
Exactly.
Easier for artists to deal with.
It kills me that this even exists, but it's just a necessity at the moment. And so, like Kelsey said, these values are all the maximum things that were encountered as you moved about the scene. And so the maximums are really what you need to put in those CVARs in your INI files. In the future, when the engine side changes a little bit, all of this will be done for you, and you won't have to reset these things. But just at the moment, that's unfortunately not the case. So this summary exists to kind of give you that information so you don't have to guess. But it also gives you a lot more info if you are a graphics programmer out there. This tells you a ton about what's going on under the hood, where the memory is being used, every frame, what's being processed and what's being done. So it is very useful from that standpoint, and will continue to exist even when we do some of these other things automatically.
Yeah, I can see Kelsey is toggling the Mega Geometry.
Yeah,
you can see it really in those vine shadows because they're so high poly. They're in the millions of triangles, and you turn the Mega Geometry off on them, and it becomes really obvious. They're no longer casting shadows in a per poly way.
One of the things I like to do is, like, if you turn the stats window off and go back to bookmark 2, I think it was.
This one?
Yeah, and then hit the visualization. So this is showing you what's in the BVH. And so if you turn Mega Geo on and off, it very clearly shows you the difference of what's in the BVH.
The tree getting lower poly.
Holy.
Yeah, so the tree's fallback proxy mesh, like I was showing those slides earlier, it is different than the full quality thing. A lot of that detail is just gone. Same thing with the ivy. The ivy just disappears because the fallback meshes really struggle to make good geometry of stuff like that. And as a result, when you go back to the lit mode, the shadows and reflections will be different because what's in the BVH is different.
Yeah, I don't know how well you guys can see this here, but the section of the tree root, right.
It's completely different.
Oh, look at that.
Completely gone.
Go ahead and hit player. go ahead and hit player and then zoom up to that.
Yeah.
And by the way, Kelsey, if you want ultimate frame rate, set your frame generation to 4x because the auto mode defaults to 2x.
Holy cow! Look at that.
That's a new change. Just so everybody knows, that's a new change with the latest DLSS 4. Is that auto? If you're set to auto mode with frame generation, it defaults to 2x even on 50 series hardware. So
300.
Yeah.
Oh
So-
my goodness.
Excessive number of frames. I'm sure you can power 4K resolutions. Pretty
What
good.
if I look up at the sky?
Right? Yeah.
Oh my gosh.
Like look at nothing.
Well, that is fairly easy to render, but
Yeah.
but
No.
if we go back and we look at the shadow and you toggle Mega Geo
Yeah,
off,
look at that.
you know, the
Yeah, see
shadow is
that
going to
right
be
here.
this very blocky proxy.
Yeah.
And you know, if you turn it back on, then it's going to be the actual shadow, even down to little tiny details. It will have all that. Your
Right.
contact shadows from the vines that you can see in the same shot, like they're all there because everything's finally in the BVH.
Right.
Yeah.
People might notice that the sun catcher doesn't change as you toggle Mega Geometry on and off, but that's because it's a skeletal mesh. It's not included in Mega Geometry. But it also shows you compatibility, like you were saying, that it's a ray traced or path traced skeletal mesh, and it's fine. It can just be a skeletal mesh. It doesn't need to be in Nanite for things to work.
Yeah, still be in the BVH, and we'll still trace it.
Yeah, but see, and here you can see it even better. So like the shadow in particular.
Yeah.
This block here, this is what you're seeing.
Yeah.
This here.
Yeah. Yeah, and you know, this demonstrates both the false occlusions or incorrect shadows and self-shadowing happening. So if you look at the vines, the incorrect self-shadows on many of these vines, go back to where you were looking, where there's like a direct light.
Actually, here's a good one right here. We can actually 2 is better. Here. Okay.
Yeah, you'll have to get kind of close to see the false occlusion, but
like that.
there you go. Yeah, and kick it off. Well, in this case, there's no false occlusion because most of the geometry is not even in the BVH.
Right. You can see some shadow mismatch going on, though, when you looked at it closely.
I think what
you're
you're really referring
tree, right?
to is the tree, right?
Yeah, you can see both of these things. Yeah, so like here, the proxy mesh is so different than what it should be that you get these massive incorrect occlusion or shadow areas when you try and ray trace with those proxy meshes. And you might say like, oh, well, I don't see that in games that ship with Lumen or ship with ray tracing turned on. And the reason why is because they'll add a big bias value to basically push the origin of the ray tracing away from the proxy mesh, avoiding that artifact, but in doing so, they lose contact shadows. And so you actually get less shadowing when you do this as a workaround. So the solution is to basically do what we're doing here with Mega Geometry, which is have the same geometry in the BVH that is rasterized.
I just wanted to point out a couple of improvements that came about from the creation of the scene. One of them is some improvements to path tracing performance. That'll be, by the time we get the scene out, that'll be part of the code. At least that's the intention. So people should notice that Reaster-based path tracing is a little bit faster. And if you, Kelsey, if you can go down to that mirrored area down towards the
I know what you're talking about.
Yeah.
Oh, yes.
There was another improvement here to translucent colored shadows, where so here we have the sun. You can see it. There's the mesh is sitting up there on the mirror, and we got colored shadows transmitting through the surface and coming down into the scene. But we noticed that colored shadow transmittance wasn't appearing in path trace reflection, at least not fully. So if you move your camera over slightly, you'll see that with this latest code, You might have to wiggle your camera up, but you'll notice, yeah, it's fully represented. Like path trace reflections are basically more complete now. We were sort of missing some transmittance there, and it's that's been corrected for. So I just wanted to highlight a couple of these things coming as, you know, little improvements to path tracing, but meaningful, and to help make it more complete. That's one of the cool things about doing a project like this is we start putting everything together, and then we look for problems to fix or little issues to repair. There are a bunch of, you know, just little things that come up with, whether it be mega geometry or ray tracing or whatever, and, you know, look for things like this to improve.
And everybody knows I love me some colored shadows.
Yeah, it's a great asset. It's very detailed. If you could, Kelsey, if you can go back to one of the mirrors,
Yeah.
like that one right next to the tree, and get like a zoom up on it. It just shows you how much detail is here, because like we started to see this with Zora, right? Where, because Zora is all over the place and it was doing Easter path tracing. But just how represented that reflection is, like it's capturing all the indirect lighting, all the light transport, all the everything is being captured in there. If you turn the camera around and look at the tree, it looks identical. It looks like direct rendering in a mirror. And in the past, we didn't, you know, up until this point, we didn't have that in a reflection. You would be missing indirect lighting or some other detail.
Well, go ahead and turn, like, look at the mirror and turn it off.
Oh,
So
yeah.
that's somewhat of an extreme example, because the
Right.
proxy mesh for the ivy is either non-existent or quite bad. But even if you just look at the tree,
yeah,
you know,
the tree.
the faceting and of that detailed bark is just totally different.
Right.
Yeah, it loses knots and everything. Look at that.
Yep. Yeah, the shape of that knot is completely different.
Yep. Poor birds. What if there were birds living in there?
No place to call home.
It's their
Oh,
home.
man.
Yeah.
Yep. So we're going to have this scene out soon. Like I said, we're targeting a few weeks from now, and then we'll have a follow-up episode to this one to talk about the scene in greater detail, get into the settings of it, like sort of where we landed, and we'll look at assets and talk about, you know, how many millions of triangles everything is. I mean, you know, it's pretty heavy duty.
We went crazy.
Yeah,
part of the point is to show what you can do with geometry. You can do a lot.
For reference, when I was just doing performance captures, this scene roughly at the first bookmark.
This one or this one?
0. Sorry. Yeah.
0.
Programmers first. This is rendering or putting 66 million triangles in the BVH,
woohoo,
which is around 30 times more than without Mega Geo. So
challenge succeeded.
yeah, I challenged Kelsey. I said, "Go nuts," and she did. Yeah, she very much did.
Oh wait, there was one more question I wanted to ask you, Adam. I mean, both of you really developed this scene. Adam, you were developing the technology. Kelsey, you know, you're getting the assets together and building this out. Any special advice to artists as they construct their high poly nanite scenes? I mean, what would you say? Any considerations or anything that they would need to do differently with mega geometry or nanite or anything like that?
Yeah, I think
first you know,
Adam. The first thing I'd say is, like, you're still building assets for real time. I know with Nanite, it's very tempting to say I can go nuts with geometry, with mega geometry, same thing. I can go nuts with geometry, and you can, but you're still building things for real time rendering. I assume for most people out there using Unreal, and so even though you can use more geometry, you should ask yourself whether you should. The good old Jurassic Park question. And in some cases, the answer is no. You know, you don't need to sometimes. But in the cases where the camera or the player is going to be very close to something, and adding more geometry will allow you to create a lot of nooks and crannies and details that you probably would have baked into texture in the past. That's the opportunity to say, okay, I'm going to go big with the geometry because it'll have a big visual impact and my player will be near it. And Mega Geometry will work wonderfully there. If it's an object that is, you know, going to be casting certain types of shadows that are important, that's another area where you say, okay, the extra geometry here is worth it. From the tech side, when it comes to like crafting your assets and stuff, or crafting a scene, my big advice is keep an eye on the number of unique Nanite assets you're making. So instances, no big deal, right? But that's why in the summary of the debug UI, there's this unique meshes thing. Those unique meshes are the things that contribute to your memory footprint. And so keeping an eye on how many of those you have is really important. That said, that like the number is not the only important thing. So in the next episode, when Kelsey talks about how she constructed the bonsai tree and the other trees, she actually has more unique assets, but those assets are instanced a lot. So you can end up making an asset like a tree out of fewer unique triangles than you would have if you built a single tree that was a single asset and all the triangles were unique. So you can actually get much higher quality by having a couple extra unique ones, meshes, that are then used in a very smart way. So I'd say this is totally applicable to Nanite in general, and will benefit you when you build content even without ray tracing. But yeah, keep an eye on your unique Nanite meshes and your memory footprint. And yeah, anything you have to add, Kelsey?
No, that I love that you said this also applies to Nanite, and it's so true. And another thing too, from like an artist standpoint, not like just a technical artist, but I'm talking like content creation teams, environment, any kind of content creation that you would create from like, I don't know, Maya, ZBrush, whatever. It's really important to understand that, you know, the higher poly that you're going to go, the more taxing it is going to be on your machine. So go through that high fidelity route, make it so that it looks amazing, especially if it's going to be like a hero prop, but understand that it comes with cost too during a specific workflow. Import times could change, you know, because if you're going to be importing like a 3 million, poly mesh, it's going to take a little bit of time. So different things like that you should be aware of as well.
Yeah, there can be definite practical realities. Just if you're making 30 unique meshes and they're each whatever 3 million triangles, that's a lot of unique triangles to manage.
Yes,
There's like production realities associated with that. That's
exactly
outside the memory of like whatever we're doing here in the editor, but like just like the reality of what does that mean to you as an artist is making that sort of content. I mean that can come with its own set of difficulties.
Yes.
I think this is a great motivator for why you would build things modularly as much as possible too.
Exactly.
Because each thing that you import is potentially smaller as a result. So if you do have to make those modifications, and it's like, say, a tiny knot on your giant tree, you don't have to re-import the whole thing. You re-import a piece of it.
Yes.
Yeah.
Exactly.
Thank you guys for doing this. And right after this, we're going to do our live Q&A. So everybody stick around and we'll answer your questions.
Thank you, Adam, for coming and joining.
Yeah.
No problem. Thanks for having me.
Yeah, I think it's really good people to hear directly from the person who's writing this code.
Bring us out of the boiler room and we can talk from time to time.
Yeah.
Okay. Thank you, and see everybody in a minute.